Hello, everyone. Welcome to the third lecture of the Biochem series. So today, as I promised from last time, we'll be talking about thermodynamics. Just to give a little intro to thermodynamics, let me just kind of bring in or talk about or pick up from what we have talked about last time, which I was talking about the enthalpy of the hydrophobic, I guess the enthalpy or which I guess state was favorable during hydrophobic interaction. So, for example, let me redraw. So just like last time, these whatever's inside here, they represent nonpolar or apolar molecules. Apolar. And for this one, it's the same molecule, but they're just clumped together, so that's also nonpolar, apolar, nonpolar. Nice. Now, since these molecules are in the aqueous solution, we know that there are water molecules surrounding the periphery of each of the two molecules, right? So I'm not gonna bother just drawing the precise shape of each of the water molecules. So I'm just gonna represent the water molecule as a little round like spheres. Yeah, just bear with me. And then same thing for over here. Okay. Before I start and then kind of jump into thermodynamics, let me just kind of label this one state where there are the separation of the nonpolar molecules as F. F means folded, and this is the second state, which is the B. We call it bound because in respect to these two nonpolar molecules, for this state, they're bound together into one single, I guess, clump. Now, let me see. Okay, so let's think about this the change in state either back and forth in terms of breaking the, I guess, the hydrogen bond. So see, so here for the, at least for the folded state, we do see I guess per surface area of each of the molecule, we see I guess we see I guess more numbers of the hydrogen bond formed. So formed, and then so which means that for each of the molecule, it will have I guess less dynamic uh, I guess bond orientation or H2O to movement. So this is just like analogous to the state of ice I mentioned under my last lecture. So it is less dynamic, and the bond orientation it is pretty stagnant. Also, there's a decrease in H2 movement, which means that in turn, what happens is that um, they have a stronger bond, net bond, stronger net bond. So stronger net bond. Here in the bonded state, however, per this one big chunk of nonpolar molecule, we do see a decrease in number of H bonds. So what that means is that since there's a there's decreased number of H bond, which means the bond orientation on then H2O2 movement. It's quite flexible. But however, as a downside is that they have weaker bond. Okay. Now let's connect this concept with thermodynamics. So notice that from this folded state over here, we said the net. I get so for at least for the folded state, we have a stronger net bond, and then as we transition from the folded to the bonded state, we do see a weaker amount of bond, which means that you need extra energy input it onto the folded state to break those bonds in the first place in the folded state, and then transition it back to the more loosey-goosey weaker bond state, which is essentially a bound state. So just kind of summarize what I just kind of blabbered so far is that for a folded state to bound state you need energy input. So in other words, energy must is absorbed. So we can express this, I guess, this transfer in energy between the two states as we can define that the transition as in change in enthalpy. The enthalpy. Now, since we have a delta sign over here, it means a change. So it is a delta F. I'm sorry, H. So H B. Because so that's your I guess your final output and your initial output, which is HF. And then that has to be positive because there's a higher energy state for the folded state, and then since you're absorbing energy to break the folded state, means that for the I'm sorry so you'll have a right so since you're inputting energy between transition from the two stage, you are adding energy, which means the delta enthalpy or delta H has to be positive. Sorry about the little confusion over there. Enthalpy. So if you look, intuitively speaking, when you're trying to put an energy to make a reaction happen or this transition happen, you might think, okay, that is not favorable. Like why does that even happen? And then, however, we see this this clumping together of oil when you shake the mixture between oil and water. They're pretty readily available, and then they happen spontaneously. So what actually drives the reaction from here to here? Even though the change in enthalpy proves that the whole reaction is unfavorable, well, that comes down to a question of entropy. So that's another thermodynamic biovariable. So this is just a definition because degree of randomness. Or if you study maybe advanced physics, sometimes they kind of label it as a degree of a number of conformational changes, but I will not go into mathematics for that. Entropy. Now, so you might now have a second question about, okay, since we're if entropy is a degree in randomness, and then I guess the degrees number disorders, then it seems like these two non-polar just molecules are just bound into one, and seemingly you think that, okay, well, there is an increase in order, which means there's decrease in disorder and thus decrease in randomness. However, we have to consider that this degrees of randomness occurs in a point of view of water, not the this non-polar molecules. Water is the key. So what that means is that if you look at the folded state, you see a lot of water molecules. They're all bound into the one rigid state, which means, like I mentioned, there is a less dynamic movement between the water molecules. So there is an increase in order for this, which means there's absolutely just decrease as a inverse or converse in this case. So increase in order and decrease in disorder, and then thus decrease in randomness. Now, if you look at the bounded state, actually, then there's actually a lot of water that kind of floats around, and so we're looking at this type of water that does more movement or has more movement compared to what you see in this folded state over here. So in this case, at least for the water part, we said there's an increase in randomness, thus decrease in disorder, and yeah. So if you convert this, I guess, this observation into a mathematical formula, like just entropy, what happens is that there is more entropy in the product side. So we note the entropy in delta S, entropy, and then same notation delta WHF. Now, sorry, it's like that. F. Now, since we see now increase in entropy while transitioning from the folded state to the bounded state, so that part has to be positive because there's an increase. The increase is always a change in. I get increase means the delta S has to be positive. So it's a little notation. Positive. So now you have two variables that represent thermodynamics, but how can you put this together to determine whether this transition is indeed favorable or non-favorable, or whether, in the other words, whether that transition is spontaneous or non-spontaneous? So that's why we include a third variable called delta G. This is Gibbs free energy. Gibbs free energy. And we define it, the Gibbs free energy as delta H minus delta T, delta S, like that. Note that there is some difference. I'm sure if you look in the textbook, there is a delta G, delta H naught, S naught. So this is only for when you're I guess you're trying to calculate with a spontaneity on standard conditions. But I'll try to swing that around later as I talk about KEQ and pH and everything. But let's focus on this first. This for now. Delta G. This is a really important formula. This is just the foundations on how thermodynamics works. And based on this formula, we can predict whether the reaction will go from one side or the another, or vice versa. So this formula is crucial. And you better memorize this expression for any other upcoming exams, or just like if you're interested in biochem, or if you plan to use them in like your near future. I mean, yeah, whatever you have to do. Yeah, I see. Okay. Now, as you may notice, when delta G is negative, we call that exergonic. Exergonic means it's spontaneous. Spontaneous. When delta G is positive, it's endergonic. That is not spontaneous. So what spontaneous means is that a reaction will happen without any addition of external energy or any drive that can push the reaction to a side that you're trying to push to. So it is basically it is just an automatic process that the reaction will happen no matter what, without any external forces added toward your reagents or your products. Now, if you are trying to associate the positive and negativity of delta H with the delta G with delta H and delta S, what you can build these type of relationships. Okay, now if delta H is negative, delta S is positive, then let's see, negative and positive, and T is it's in Kelvin, so it's always positive, which means the delta G is always negative. Okay. Now, if delta H is positive and delta S is positive, then the reaction is spontaneous only at high temp, right? Because it is the I guess sign of delta G changes based on this. So if this is too small enough, then this will overcome this positivity will overcome the negativity. So delta G will be positive and that's not spontaneous. So yeah, so you need to make this T as high as possible, where at high temperatures to drive the reaction to the product, and then thus make the reaction spontaneous. Okay. When delta, sorry, when delta H is a negative, and delta S is negative. Now, delta G is spontaneous only at low temperatures. And this is a same case, just like the second one I mentioned over here, right? So this is in this case this is the opposite, because delta H is a negative, which means it's gonna favor I guess a spontaneity, but you see that the delta S is negative, which means this entire part will be positive. So you need to have a temperature as small as possible for this negative one to overcome this positivity, so that the overall reaction, or I guess the overall expression of delta G can be negative. As a last combinations of variables, we can just state the last one. So, and delta H is positive, and delta S. Let me see. Wait, upon. Okay. Right. If that is the case, then delta G is always positive. So it is never spontaneous. Okay. Yes. And I'll leave the reasoning why that's the case to you audience. Spontaneous. Oh, okay. Oof. Alrighty. Now, let me just briefly mention what I stated before about delta G naught and delta G. So delta G, like I mentioned, so this one is only for standard cases, standard conditions. And we can actually rewrite the expression of delta G naught on standard conditions as delta G naught is negative RT ln KEQ. So if you remember maybe your AP chemistry or your general chemistry knowledge, kind of bring that up. So that's RT ln that's product over reactants. Sorry, for reactants. So reactant. Okay. Just like that. Okay. However, so notice that KEQ so basically so that's a ratio of product and reactants when it's in equilibrium condition. Equilibrium condition just basically means that the concentration of the product and reactant are stagnant, but the reaction is still going on. So there is some set ratio between the product and the reactant. Or in some time after the reaction has started. So so that's how you express delta G naught, which is as expression in negative RT ln KEQ as standard condition at equilibrium. So there is this big difference between delta G naught and delta G. Delta G, on the other hand, we express it as delta G naught, the equilibrium STD, standard condition, STD condition, plus RT ln product over reactant. Now notice that the while I mentioned this part, it's at the equilibrium setting, right? So but this one, that's the initial setting. So what that means, it has some substantial conclusion, is that even though if delta G naught as standard condition is positive, by changing the number the ratio between product and the reactants when the reaction first starts, you can actually shift the entire reaction to be either positive or negative. So that's a really profound implication of this reaction. So make sure to remember this reaction as well, because this becomes really valuable. And sometimes a lot of professors they like to ask some trivial math questions using this expression. So you don't want to miss any points from that. Right. So nota bene that even though delta G naught as positive, delta G naught can be negative, does drive the reaction. Sorry, two products by altering the ratio of product over reactant at the start of the reaction. Reason why I mentioned the ratio of the product, just to kind of give a little a recap of the pre-cal. So if you change, I guess the ratio maybe 3 to 1. So this is in the log form, right? So that will has to be positive, or yeah, positive, positive. So bigger than 0. When ln is maybe ln is 1, 1. But for example, if there's a log form, right, the exact ratio is 1, so that becomes 0. So what that means is that sometimes if there's an equal concentration between product and reactant, so this entire thing becomes 0, which means delta G. This is a special case. That's when delta G equals delta G naught, when the concentration between product and the reactant has to be equal to each other, so that this entire part that's a log form becomes 0. So this is a really important concept that you also want to remember as well as this, because for this one I've seen some professors kind of what they're trying to trip people somebody up by asking this this sort of a concept. So make sure you don't forget about this little trick or this special case. Okay. For for my next lecture, I'll kind of give a little introduction on amino acids and how the amino acids I guess forms depend on the pH of the solution the acid or amino acid is located in. So I'll try to bring in the concept of pH, pOH, and just some different structures or a list of amino acids. And then some of their unique characteristics that you might be wanting to know about. Okay, so that is all for today, and thank you so much for tuning in.